So I'm going to this talk is going to be an overview of some of the things we've done with quantum computing for finance. And what I'm trying to do in this talk is I really want to introduce a key tool in quantum computing, which is quadratic unconstrained binary optimization. So I'll introduce that and then give some examples of how we've actually applied this to finance. Um, so a little bit, first of all, about multiverse computing. We're a Spanish Canadian startup. So we're based in San Sebastian and Toronto. And then we also have offices in Paris and Munich. So we're currently Europe's largest quantum software company. And what we really like to do at Multiverse is we really like to focus on real quantum solutions for real world problems. So this is actually developed rather than hypothetical algorithms which may work in 5 to 10 years. We really like to find solutions that can deliver value today. And we're completely hardware agnostic. So this means we work with all of hardware backend vendors to try to find the best hardware which can solve the problem. So we at Multiverse, we really pride ourselves on our academic excellence. So our team has over 9,000 plus citations. Our CSO is Roman Orris, one of the world leaders in tensor networks, and in quantum many-body physics. And our team is 40% PhDs, and then everybody, a lot of master's students, as well as really high-achieving interns. And then also, we really pride ourselves on diversity. So currently, our company is 30% women, and then I think 23 plus growing nationalities in the company. So we're a super diverse company, and we really, really like to celebrate that. And finally, if this talk interests you, we have summer internship positions available, paid summer internships. So I think these are available in Spain and Toronto. So go ahead and go onto our website, find more details, and apply. It'd be great to meet you in the summer. So as I mentioned, what we're going to start off with is an introduction to qubos. So why are these important to quantum computing? And then introducing the concept of building basic cubo problems. And then we're going to build up to actually applying this to finance. And then finally finish off with a little summary on how we can actually apply this beyond finance, so to other industries. So why do I want to focus on quadratic unconstrained binary optimization? This is a really important tool in quantum computing. And this is because it allows us to map optimization problems to binary variables. And obviously with binary variables, we can use quantum computers to represent these, and then we can solve our problem. So we really like this because a lot of really hard discrete optimization and combinatorial problems, which are NP hard, can be represented in the form of qubos. So this means we can actually find really valuable solutions using quantum computers right now that you can't actually do with classical machines. So this is a really important thing, which I like to focus on the qubos, is because this is a technique which we can use to provide real value using quantum computing right now. So if you think about a lot of gate-based quantum computing algorithms, to actually get a fully working quantum Monte Carlo, we're going to have to wait at least 10 years to get enough resources to run this. Whereas with qubos, we can actually use real hardware now to solve these problems. So it's a really nice way to solve these problems as of now. And then, so qubos naturally occur in quantum physics. So this is in Ising spin glasses, and if you think about any quantum systems where we've got to align particles, and like in magnetism and materials, all of these problems kind of derive in physics. So a really nice thing is then we can use quantum effects to solve these problems. And as I mentioned, this is really nice because the qubos are a general form, so it's down to your imagination. How can you construct your problem into a cubo, and then you can use a quantum computer to solve it? So this can be applied to many applications. So it's really a versatile tool. So before I get into constructing a cubo, we're going to touch upon briefly how to the hardware to solve these. As I mentioned, right now we can use quantum hardware to solve these problems. And if you're probably very familiar with quantum annealing devices are the most promising way to solve these because they can naturally embed the form of the problem. And we have D-Wave and QCI, which are both offer really powerful quantum annealing devices. Then on top of actual using quantum devices, we can actually also solve this using tensor networks. So we can use these techniques from many Bosy physics to use tensor networks, which can solve these using classical hardware to basically simulate quantum effects. So this is something at Multiverse we specialize in developing our own solutions for these. So just a really, really brief, I'm going to give you less than a 5-minute introduction to quantum annealing so you can understand, how the qubos fit to solve these problems. So with quantum annealing, what we do is we start with an initial Hamiltonian. So this is generally just an initial state, which is really easy to prepare and has a known ground state. So a known zero energy solution. And then the idea is that what we do in annealing is in the left-hand side of the equation, we slowly transition to the right-hand side of the equation, which is then the form of our problem. So we can actually see in this nice little graphic here, if we start in a solution where the ground state is known, so this is usually the equal superposition of everything, we then slowly and smoothly apply the adiabatic theorem of quantum computing says that we'll stay with very, very high probability in the ground state. And so we can see in this graphic that as we slowly evolve our system to our cubo problem, we hopefully stay within this range of having our optimal solution here. So this is why quantum annealing is a really powerful technique for solving these problems. So if we look at the right-hand side here, this is how we want to embed our problem. And we can see this involves terms of, we call these the HI terms on-site terms, and then we have the J terms, which are coupling terms. So the on-site terms are where we apply a value to just a spin on a single qubit, and then the coupling is a spin between 2 qubits. So a really nice example I like to start off with to get your head around this is if we think of a classical signal system with magnets. So if we want to have, say in this example, we've got 3 magnets and we want to have them in place, we have to align them in a certain way. So if we have south, north, south, they all attract together. And we can call this a zero energy state because I don't have to apply any energy to hold these in place. And then if we go above that, we can see that, if we have one magnet the opposite way around, I'm going to have to apply a little bit of energy now to hold this magnet in place. So in simple terms, what you can think of this being your qubits in your system. So these qubits are kind of spinning around and we're applying our forces. So we're applying our fields. So this would be our on-site terms and our coupling terms. And we want to make sure that, the magnets are all aligned properly with the least energy. And here we've got an example of when we're applying the on-site terms. So in the previous slide, this is kind of where we're looking at the coupling terms. So the interactions between magnets next to each other. And then we can apply on-site terms as well. So you can imagine that we have a system of magnets where I'm just holding them over the top. So now we've got to make sure they align well with each other in this coupled system, but then they also align well with the on-site terms as well. So we can see here that configuration 2 would be where all the magnets are aligned with each other and I don't have to hold anything in place. So this is a really nice example to get your head around the basics of what quantum annealing would be doing and how it's going to try and optimize these systems. So now introducing the cubo. So what is a cubo? It's actually very simple. And it's basically an upper triangular matrix of coefficients. So we have our on-site terms here are h's and our coupling terms j. In our cube matrix, we can have our on-site terms along the diagonal and then our coupling terms on the off-diagonal terms. So then when we're applying our variables, to this operator, what we end up seeing is we get this nice quadratic equation. And this looks very simple, so you're thinking, how can this actually solve problems? And there's many tricks we can use to start encoding complex problems into these binary variables in a way that we can make use of quantum annealing to solve them. So a really nice example to start with is the knapsack problem. So with the knapsack problem, what we start with is we have a set of items, and if each of these items is assigned a weight and a value, and then we have a total weight budget in our backpack. So we want to pack things with high value, but obviously we want to try and optimize so we're not carrying too much as well. So we can see here, I've just put some arbitrary values. These are items we may want to put into our backpack. And what we can do here is with our binary variables, we can assign each binary variable, so a 1 or 0, yes, I want this, no, I don't want this, to each of these items. So then we can pose this as a cubo optimization problem. And then there's another nice trick we can do, is that we saw there were quadratic terms, so we can add some extra complexity already. So we can have an interesting term that if we have a can, then we really need a can opener. So we can have like these quadratic terms here, which define the interaction between two variables. So if I have x2, then I need x3. Otherwise, this isn't going to be minimized. So as I mentioned, we've got our values and our weights, which we're going to try and maximize our values, but make sure our total weight is constrained less than our weight budget. So we can formulate our cubo as I've shown above in this nice simple form here, but obviously this doesn't take into account the constraints. And this is what really makes the problems difficult, and it's a really powerful technique to start putting these constraints in. So how do I include these basic constraints? So we can start off with the idea of an equality constraint. And it's actually very simple to include an equality constraint, because we can form this naturally into a quadratic term. So if we have our weights, what we can do is we can sum over all of our weights multiplied by their binary variables. So if the object was included or not, and then we can minimize this quadratic term here. So where b is our total budget, and because it's quadratic, we're going to have this nice curve. So we know our minimum is going to be when this sum equals b. So when we're doing the quantum annealing, it will minimize to when this constraint is held. Otherwise, there'll be some positive energy in the system. And then going a little bit further than this, in the knapsack problem, we said we wanted it to be equal to or less. So how do we include these less than operators? To do this, we include something called slack variables. So these slack variables are free variables in the problem. And the idea here is that based on the configuration of the objects and weights we include, the slack variables can make up the difference to get to the value b to minimize this convex curve. So in this case, we have our slack variable running from 0 to b, and then we let the optimizer freely choose this based on our optimal solution as well to make sure that we have something which is allowed to be less than our total budget as well. So if we're putting this all together, we have the final knapsack problem with our nice little quadratic constraint here. And we can see that we get this formula with our binary variables xi. So the way then we turn this into our coefficient matrix is we have to expand everything out. So you could do this by hand, but is there an easier way? So one of our core products at Multiverse, which we use, is Singularity optimization. So the idea here is that we have an interface where you can define your problem without even having to worry about the quantum variables or the quantum solver behind everything. So for our knapsack problem, what we can see here is that all we have to do is simply define our variables, our cost functions, which is going to be our profit and our weight. And then we can automatically define our constraints and then set this as our objective to minimize. So this will automatically handle all of that laborious expansion into the qubos, form it into a way that is efficient for the D-Wave solver to solve, and then we get back our solution. So moving on to finance. So how can we relate this to finance? The first step is, if we think about this naive portfolio optimization, we can think of this as a knapsack problem. So if we have a universe of stocks, they all have a value, and they all have a value and an expected future return. So if we have a budget, say I have $1,000, how can I select the amount of stocks I want to maximize my future return, but to stay within my budget? So we can see that this is directly related to the knapsack problem. And if we then wanted to say, well, I want to buy more than one stock, we can apply this to the knapsack problem as well, as we can use a unary encoding scheme. So this is simply saying that we can associate more than one qubit now, more than one binary variable with each asset. So here we can say that we're allowed to have 2 of each asset in our portfolio, and then we can solve it in a similar form to the knapsack problem to find how many stocks to hold within our budget. So this is a nice simple example of relating from the knapsack to portfolio optimization. But in general, we want to find a more general and flexible form. So to do this in portfolio optimization, we come to the Markowitz portfolio optimization formula, which we have here, where we want to find a set of asset weights. So we can have these as a discrete set, or we can approximate a continuous range of values. And the idea here now is the same. We want to optimize our returns, but in this case as well, we're now also including risk. So obviously investing is risky. So we want to make sure that we're minimizing the variance in our portfolio. And this includes the covariance between assets as well. So we want to make sure we have diversification. So now we have this set of weights. We have to apply some more constraints to it. So the first constraint is we allow no short selling. So all of our weights have to be positive. So we're only allowed to buy stocks. And then the second constraint is no leverage. So this is an equality constraint. So we have to make sure that the sum of all of our weights equals 1, so that we can fully invest our total value. And then we can apply this portfolio to any budget. But there's also a nice extension actually in the literature where, if you have a small budget, you can include this budget term here, B, in a similar way to the knapsack problem, and you can optimize your weights here. So then the next technique I'm going to touch upon is, how do we encode? Well, I said these can be any values. Now, we're not looking at just zeros or ones. How do we encode that? So what we can do is we can include this as a binary expansion. So in this term here, we can have our binary variables, and we are now associated with a power of 2. So this is your standard binary interpretation of numbers. And we can then encode our weights. If we have a total of investment units, we can then encode our weights in this form here, where we're going in increments of 1 over k, and we can define this using our integers defined by a binary encoding. So then we can see now that we're having more than one binary variable associated with each asset. So then if we look how our cubo would be formed, we now have this diagonal operator here, where we're having different values associated with each qubit, but there's sets of qubits associated with each asset. So then again, I don't want to do all of this by hand. So we can use Singularity optimization to handle this for us. And the key really here is that we can use this SOP integers, which will automatically handle this encoding and find efficient forms to encode our integers. And then we can, as before, create our problem and use this create our problem and our constraints and solve this using any of our quantum backends. So before we end, I really want to just highlight a few more other tricks and constraints we can come to you can take away and maybe apply this to your own problems. Is before we were limiting our integers to anything which is a Mersenne number, we can extend this using this formula here to encode any integer value possible. So this allows more flexibility in the numbers. And then there's other constraints we can apply and to make our problems more efficient. So like banded encoding, where if we need at least 5 assets in our portfolio, we can limit the range of our integers we're looking at. We can limit the range of our holdings to automatically encode these. So if you think about making a cubo problem, you can always think about how can I encode my constraints directly in the encoding of the problem. And then finally, another really interesting constraint is using sector constraints. So if I have a portfolio and I want to invest in tech or manufacturing, you can group these assets and then apply these slack variable inequality constraints to say how much I want to be in this sector. So then beyond portfolio optimization, there's some really interesting applications which we've worked on, which is dynamic portfolio optimization. So now we have more than one time step, and each of these time steps is dependent on the last time step with transaction costs. So if I'm changing my holdings between each of these time steps, that's going to cost me. So this becomes a really, really complex problem now because we have variables in time and our asset space as well. And this problem is very, very difficult to solve with a huge search space for classical computers. But again, using the cubo formulation, we can use quantum annealing to efficiently solve this. And then another interesting application we've worked on is index tracking. So if I have a large asset like the S&P 500, how can I track this index by only buying 50 stocks? And this is a challenging non-convex problem because we then have to have this indicator variable to say, I only choose 50 stocks to invest in. So in this case here, we've got this Z variable here where we're conditioning it on the assets being held. So these are really interesting ways that we can extend the portfolio optimization problem. And then where can we go beyond finance with this? As I said, these are really powerful tools that we can use to solve many problems in many different industries. And one of the flagship applications D-Wave focuses on is also the traveling salesman problem. And we also do some work on network analysis as well. So the idea here is that we can map graphs to our binary vectors. So we can map our edges to a binary vector, and then we can solve these problems to find our vector of edges we included. We can also include define graph coverings, so we can include edges and nodes. So there's really a lot of ways that we can encode these graph problems. And then obviously we can map these graph problems to any domain you're interested in. And then finally, there's a really nice also focus on how can we build qubos for machine learning. So there's some really interesting work using quantum boosting. So this applies qubos to form regularizations which you wouldn't be able to solve efficiently classically. So we can do that using a cubo and solve this using quantum annealing. And then there's some other interesting work where they look at optimizing binary neural networks. So these would be not smooth functions which you could optimize using your classical optimizers. So how can we use quantum annealing to solve these discrete weight problems for machine learning? So really, you can use your imagination, go crazy, and the art is just how do I formulate these problems? And I really hope that I've given you some tools to start thinking about how I can encode these problems, and you can go away and start building your own qubos and try running them and really learn how to apply quantum computing. And then if you're interested, I've got a list here of some of our applications at Multiverse where we've recently published, and all of these focus on where we've used qubos to solve our problems. And so, yeah, thank you very much for listening, and good luck on your quantum journey.
Thank you so much. It was really fun. I love seeing some of these classic problems, coming back in to the quantum world again, and applications of finance is pretty exciting. Um, Before we get into a couple of serious questions, which we do have in the chat, I want to ask about butterflies.
Yes. So yeah, it was during my PhD many years ago. Um, tech, I had to get away from technology, so I decided to go off and join a volunteer program in the Amazon to research butterflies. So I think this was almost real life Pokemon. You know, running around catching them, and then everybody was get really excited when you find one we haven't found in the area before. So yeah, that was really great.
That sounds so awesome and such a fantastic way to get away from technology for a while. I'm a bit jealous, actually. I do have a couple of serious questions from the chat here as well, though. So the first question from Jackie Root. Hi, Samuel. If Kubo is where quantum computing can provide real value right now, doesn't that mean that quantum computing is already better than classical computers?
So that's a really good question. I mean, I think the point there is to say that there's some caveats with quantum annealing. So the main caveat is that to form our problems, to map them onto our architectures of our quantum devices, we kind of have to go through a graph problem already to do that mapping. So sometimes there's this question of, okay, you have to solve an NP hard problem to solve this problem on a quantum device. But as the architectures are improving, so D-Wave is introducing more connectivity in every generation of their devices, this becomes less of a problem. So we start really seeing the advantage. But I think the thing we like to focus on is, rather than there, arguing if there is or isn't a quantum advantage, we like to say that there is a customer advantage. So, even if you could solve this on a classical computer, you can still solve it quicker on a quantum device or more efficiently on a quantum device. And it's also setting yourself up for when the technology has really matured to that level of quantum advantage, that you can just apply these problems directly onto that.
I really like your customer advantage term. That's yeah, it's a really a really smart way to think about it, actually. Um, so a second question we have is, would you say that optimal penalty coefficient selection for constraints modelization into Cubo is solver agnostic? This is from Antonio Jesus G. Sorry.
Yeah, so this is an interesting one. I think again, this is solver agnostic in terms of, if you're setting your constraints up right in your penalties, then it doesn't really matter what you set your penalty values to, because you're always going to get to the minimum zero. But I think you do have to sometimes make sure and think about the connectivity of the device you're embedding on, to make sure that these penalties are tuned that the correct interactions are kind of penalized more than others. So there's some, you do have to think about how can devices handle certain constraints better than others, and maybe the mappings, but usually don't have to think about too much about that. That's the very, very, very niche, and you can usually just play around with the values slightly to find something which gives you a solution.
Mm-hmm. Yeah, and maybe a slightly related question. What are some of the most promising classical optimization problems that we know quantum has advantages for? This is from YQCat.
Yeah, so again, as I said, like I won't say quantum advantage, but I think we see the real power, as I said, was in these. So D-Wave, really their flagship application when they first came out with their annealers, was the traveling salesman's problem. So this is the idea where you've got to find optimal logistic trajectories. So this is obviously this is an NP hard problem, and this is something which you can solve very efficiently using quantum annealers. And again, this is similar to the knapsack problem as well. That is an NP hard problem. And again, as you saw, we can make this a cubo and solve this very efficiently. And this has a lot of applications to, as we've seen, to finance and any other applications where you've got to do these kind of allocation-based problems.
Awesome. Well, thank you for answering all our questions. I think that's all we've got time for. There are more questions here, and I believe your colleague Praveen is going to be available on Discord later. So
Yes.
maybe any extra questions can go there for now. Thank you very much, Samuel, for being with us today.
And thank you for having me. And yeah, as I said before, good luck everybody on your quantum journeys. And if this has excited you, please apply to our summer internships. And you'll learn a lot more than what I presented here. And yeah, it'd be great to meet you.